This is Dr.Aravind Rajan Ayagara from the Aeronautical Department. I'm an associate professor at the Institute of Aeronautical Engineering. In the last class, we were seeing what are the avionics subsystems that are present in an aircraft, and we also watched what are the navigation systems that we have used. To have a small recap, we have ground-based navigation system, we have inertial air data sensor-based navigation system, and we have the global satellite positioning navigation system. So each of these three navigation systems have been evolved since their usage in the First and Second World Wars. So the first thing was ground-based navigation systems, where we had beacons that were present on ground, which were used to take the aircraft from one waypoint to other waypoint. Waypoint are nothing but one position to another position. Okay. We also have seen what are the different parameters dealing with aircraft navigation systems, such as aircraft's true heading, magnetic north heading, true airspeed, indicated airspeed, that means Mach number or nautical miles, and also we have the altitude, which is given from the barometer. And using these parameters, we can actually convert into the local aircraft velocities in Vx, Vy, and Vz directions and everything. And the second navigation system that we have seen was actually on air-based air data or inertial sensor data-based navigation system, where the aircraft doesn't use any kind of beacons that are present on land. It actually relies on the sensors that are present on board the aircraft, such as gyroscopic sensors and the air data sensors. In the third and the latest latest navigation system that we are using is based on global positioning satellite system, where you have either GPS, which works with 8 satellites that are rotating around the Earth all the time, or you have the 12-channel GNSS global satellite system, navigation satellite system, which uses 12-channel to uplink and downlink data. And today we will be dealing with the second navigation system, second part of avionics system, which are nothing but flight instrument display. Similar to its counterpart, the navigation system, there was a revolution in the year 1970s, or in the beginning of 1970s. And prior to 1970s, they actually had used cathode ray tubes as displays, and the crew members, that means the crew which were in the cockpit, were actually pilot in command. You had the first officer and a flight engineer. So you'll be seeing where do they sit and whatever, everything. And after 1970s, the revolution actually they started using active matrix liquid crystal display screens. And due to these revolutions, or the advanced technologies that were being used in the display systems, the crew member had been reduced from 3 to 2. And during this revolution, we also know that Airbus and Boeing are the two competitors in civil aircraft industries. So during this revolution, the Airbus systems or the Airbus aircrafts actually used the electronic centralized aircraft monitors, that is ECAM systems, and the Boeing aircrafts actually use the engine indicating and crew altering systems. The only thing is, the difference is the way they function, but their responsibilities are almost the same. Okay, today we'll be dealing, and we'll also see what are the first, second, and what are the different kinds of display systems that are present today, and a little bit history of them. When you see flight display systems, you actually have electromagnetic era, you have the electro-optic era, and the next generation flight display. Next generation flight display is not yet put into use; it is in development, and we can envisage it to be put in use by 2030s. Okay, so in the electromagnetic era, we will see what was the evolution that had taken place. So we have 3 important years: 1918, 1929, and 1970, 70. So dealing with the first generation systems, the electromagnetic era systems are known as first generation display systems. We have the embryonic primary flight display system, which was actually put forth which was developed and patented by Smith & Sons Technologies, now which is being integrated into Honeywell Aerospace. And where you can see is you have a pressure data set or a barometric altimeter. So the display system that you see, this is the principal flight display system, which was the first flight display system that you use. And you have a pitch axis which is filled with some liquid, and when the aircraft pitches up and pitches down, this liquid actually moves up and down. And to its left, you have the barometric altimeter, which measures the altitude of an aircraft. And on the right, you have the time indicator, where each indicates the local time, not the local time, the time with aircraft's origin. And you also have the engine RPM on its left, and you have the barometric airspeed indicator. So this system for its day was actually a revolution. It was revolutionary. And it also has a small incolometer, which actually measures the roll moment of an aircraft. So you have the rate of climb, which is done by pitch axis, and you have the roll, which is measured. But the only con or the disadvantage is that this system actually lacks a compass. So coming to it, in 1929, you have Lieutenant James Doolittle, who had developed a system which consisted all these three. And I'd rather say this system that we look today, the system which we use today, the inertial navigation system or the instrument flight system, is actually based on this Doolittle system. So Doolittle system actually relies on a couple of gyroscopic instruments and also radio navigation aids to show the position of the aircraft for its display. And you have two different kinds of displays. The one over the top, which is inside looking out, used by US and other aircrafts, and the one outside looking in was used by Soviet Unions, and I think it is still in use today. The only difference is the way the the horizon and the sky are represented in the systems. For example, if you see the system inside looking out, you have the aircraft which is represented by its wings and its body like this, as I've marked in the presentation. Aircraft is fixed. When you roll an aircraft or pitch up an aircraft, the horizon, which was actually fixed locally to the aircraft when it was on ground, moves. So that is inside looking out. That means it is like your inside coordinate is fixed, your aircraft is fixed, and the earth is moving respectively. I'm just giving a blunt example, but this is how it works. Literally speaking, that is what we see. And in the second kind of system, which is outside looking out, I'll erase this, it's better to erase this. Outside looking out, looking in, you have the horizon, which was fixed to the aircraft. That means the horizon is actually fixed. When the aircraft moves, the symbol that represents the aircraft, the black one over here, actually moves. For example, if I'm rolling to my left, I'm rolling to my left, the aircraft symbol actually moves from steady to left. And if I'm doing another counterclockwise motion, the aircraft symbol moves from like this. So the orange one is superimposed. So okay, it actually moves. So the only difference is in the first system, the aircraft is fixed, but the horizon and the orange and blue markers, the things which represent the horizon and the land and the sky actually moves, or the horizon, the black line, solid line moves. In the second one, the black solid line is constant, but the aircraft figurine moves. And this system actually relies on the Colsman precision altimeter and also a perigyroscopic artificial horizon. This perigyroscopic artificial horizon is the one that you see that I'm marking right now. That is this perigyroscopic horizon, which is related to its analog display that I have circled. In the first generation system, you also have other systems which were developed by Boeing. So, for example, what you see here is the system that was used in Boeing 777. As I've said, this one is the pilot in command seat. This one is the first officer. And here is the flight engineer. So as you can see, this system is actually quite complicated. It has more instruments that have to be read by the pilots. So that is the reason why we have a flight engineer who is concerned, whose job concerns the instrument panel that I'm highlighting right now. And you have the engine instruments and autopilot control panel that are situated in front of pilot in command and the first officer. And you have the basic T set of primary instruments. That means you have your horizon display over here, which measures the altimeter. You have the true airspeed on the left, and on the right you have true airspeed, and you have the navigation, so on, which is in whole and sole control of the first officer. So this revolution was actually, the revolution that had taken place in the year 1970 was to actually omitted the use of flight engineer in an aircraft cockpit. So flight engineer do not exist after 1970s. But before 1970s, there were flight engineers. So in the next class, we'll be seeing what are the second generation display systems that we are currently using in an aircraft. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.